Hi, my name's Lukas Dillingham. I'm with the Aerospace Corporation in the Embedded Control System Department. I am presenting Kr8ken, ensuring embedded software resiliency through containerized DevSecOps. Need to give a shout out to teammates on this project. Andrew Melnick played a very large role on the Kubernetes side of this. I worked more on the embedded side of this. Also, Pat Doyle, Ron Rodriguez, other teammates who I guess aren't lucky enough to be on this list as well. So this presentation, I'm going to go over some background information, some motivation behind this project. Going to talk about what CI/CD is. People have talked about that, but I don't think it's been defined clearly yet. Probably a lot of you know what that is, maybe. Going to talk about the design and architecture of this Kubernetes device plugin framework. And I have a little video demonstration showing this pipeline interacting with some CubeSat hardware. So a little background information, just so we're all on the same page here. This project highly utilizes Kubernetes and containers. So a container is a lightweight, standalone, executable package of software that includes everything you need to run an application. Kubernetes is an open source system for automating deployment, scaling, and management of containerized applications. Kubernetes is often spelled K8S, hence the name Kr8ken with an 8. So the motivation behind this work is that Kubernetes has had enormous benefit for ease, speed, completeness of testing on web and cloud native code. More and more build, test, and verification validation activities are moving to these software factories in Kubernetes. However, embedded software development and testing is kind of lagging behind this area. Often embedded software engineer needs direct access to their hardware. You know, you might need logic analyzer or probe or what have you, and you need to sit right next to the hardware. The issue with this is it's difficult to scale this up to a proliferated constellation level of development and testing. So Kr8ken provides a Kubernetes device plugin framework to connect embedded hardware to a Kubernetes cluster. With this, you can potentially scale embedded hardware development and testing up to whatever level you require. Potentially connect hardware in the loop equipment to a Kubernetes cluster as well. And this opens a door for remote development and flight-like testing on actual embedded hardware. So just kind of briefly what CI/CD is. So DevOps is a methodology that integrates software development with IT operations with the goal of shortening systems development life cycles. It's a set of practices, tools, and culture of rapid feedback, small work batches, and a focus on providing streams of values to stakeholders via software. This is done by breaking down the walls between developers and operators. And this is primarily done through the heavy use of automation. So whenever there is any change to your code base, some automated process builds it, tests it, validates it, accredits it. This is continuous integration. That process can then go on to deploy it and that is known as continuous delivery. So DevSecOps then incorporates security into the mix as well. And again, anytime there's any change in your code, you do a complete scan on everything, make sure that all requirements are met on your code, there's no vulnerabilities, and this is done automatically instead of some periodic or on-demand manual review. GitOps then takes this even further, and you encode your infrastructure and configuration of cloud hardware and resources in some version control. And whenever there is a change to any of that, you again do a full automated scan review of everything and make sure everything still works. And in any step of the way, if any issue comes up, people can take action to resolve that problem. I'm going to skip this slide. So Kubernetes is a very common way to run such CI/CD pipelines. And Kr8ken then is a way to link embedded hardware into such a pipeline. So about Kubernetes, when you deploy something in Kubernetes, you can specify what resources you need. For example, amount of CPU cores, memory, disk space, whether those resources are persistent or not. And Kubernetes schedules workloads based on availability. You don't have to manually say, I want to run it at this time or whatever. So Kubernetes can handle all that for you. Device plugins then allow you or extends this idea of allocating resources to hardware, and this is usually used for things like GPUs or FPGAs. So like if you have some machine learning application, you can say, I need to run this on a GPU, and Kubernetes can find those resources and run it for you. You can also use these device plugins for any hardware, including hardware in the loop, test equipment, or embedded software, or embedded hardware, sorry. And once you integrate this hardware into Kubernetes, you get all the advantages Kubernetes offers, such as queuing, deconfliction, and load balancing. And these device plugins are just another container running in Kubernetes. So it doesn't really add too much complexity to what's already there. So then you can have this hybrid cloud setup where you have some hardware in data center or public cloud, and also on-site hardware that people can physically interact with as well. And once implemented and deployed, any tool that is already in Kubernetes you can use. So for example, Jenkins can build flight software binary and deploy it to hardware and then interact with it in some way. Or you can have an interactive workspace where you can debug on actual embedded hardware. So we've developed library and templates to simplify the development of these device plugins. So these plugins are hardware specific. So for each board you have, someone has to make a device plugin so Kubernetes knows how to talk to that hardware. But we've abstracted away the integration with Kubernetes, and hopefully that simplifies things and allows the person working on the hardware to just work on the hardware, not fiddle around with containers and Kubernetes so much. So far, we've made 2 plugins, one for Virago, that's ARM M4 processor used in Aerocube, that's Aerospace's CubeSat program, as well as a PowerPC processor. So in our current setup, we have this hybrid cloud where virtual machines can do a lot of the processing in this pipeline. And then you have 2 servers with this embedded hardware attached to it that you can access through the cloud or on site. So kind of a lot going on in this slide here, but this shows a comparison between 2 architectures. So on the left, you have your traditional microservice cloud native DevOps. And in blue, on the right, you have your embedded DevOps with Kubernetes and Kr8ken. Can I get a laser pointer here? Right, so someone develops a microservice and they want to test it. Typically what happens is some DevOps controller like Jenkins will say, I need to run a set of containers. Kubernetes will determine where those containers can fit. These components called kubelets, which run on each server, one will say, oh, that container should run on my server. It creates that container, then informs Kubernetes that container was made and gives it all the context information needed so that the Jenkins, for example, can use that container. So then Jenkins might check out code, run a build, run a test, make any archives, what have you, log everything, and once done, it frees up the resources it was using, and another pipeline can then use that. And so if you scale your amount of hardware and resources here, you can increase the number of pipelines you can run, and in turn support more and more developers. So looking at the right here, you see like this portion is the same as this. There's a couple more pieces in place here. One being this device plugin, and this other being the test hardware. So same process happens here, except when this kubelet goes to make a container, it might say, oh, I need this real specific piece of hardware. It goes to this device plugin, and this device plugin supplies all the context information needed. So when this container is made, you can access this hardware. So again, this device plugin is just another container running with Kubernetes. You'll also notice there's this other person here who needs to make this device plugin, needs to develop it. This guy here, that was me in this case. So I'll go into a little bit more about what actually is in that plugin. So I'll switch over to this video here showing there we go. All right, so I have a Jenkins pipeline here. I'm kicking off a job. This checks out the latest commit on flight computer repo for Aerocube's flight computer. Going to pause in a couple places here. So you can see me trying to highlight this. So this is showing that this job was successfully assigned to a computer. So that is where this device plugin is running and this hardware is connected. So the device plugin is telling Kubernetes, like, this is where I am. You run me here if you want access to this. So if that device is unavailable, you might see that it was not successful to assign that. This is kind of the raw output of console output of this pipeline here. So this, yeah, we check out the code here. Here's some CubeSat hardware we're actually interacting with. So there's this green breakout board here. On top of that, you have a flight computer. Top of that, you have an attitude control board with some reaction wheels connected to it. You have this programmer connected to the flight computer, and this is just connected over USB to a computer in the background there. So what the device plugin is actually doing is well, first is written in Go. So there's just this little Go executable that looks at the USB ports on the machine it's running on and sees if that programmer is connected or not. If it is connected, then it's possible that on the other end of the programmer that there's a specific processor that it's looking for. So it uses some JLink software to look at a couple registers on that processor, and it reads off an ID code of that processor, verifying that it's the hardware we want. And that is all reported back to Kubernetes saying this processor is available here. So then a pipeline like this can use this hardware. So going back to just kind of overview here, there's different components of this pipeline you can use. Builds the code. There's a security scanner on it, which takes a while, so I'll skip through that. There's a test. It deploys the code to the binary to the board, and then we have a test framework wrapped around some ground software. So we send some ground commands up to the satellite there and parse the replies back, making sure everything's okay. And this should send 18 or so commands to, for example, get the attitude control board out of bootloader, flip some lines powering on the reaction wheels, and just for this demo, kind of spin up these reaction wheels a little bit and stop it, and make sure that that all completes successfully. Skip through here a bit. So this is done with robot test framework. So you can see this is just the output to some ground software we have. So you can see for each command it's saying pass. So once this is all done, you can, whoever wants to, I guess me in this case, can look at the logs of this, make sure everything's all okay. And then all this resources is freed up and another pipeline can run and use it, someone else, for example. So I think that's all I have here. I'd be happy to answer any questions. Thank you.